Okay, tonight's notes are electronegativity and polarity. Okay, there are two types of covalent bonds. Now we have polar covalent and nonpolar covalent. We're going to have to use a little bit of math here. So to figure out if a bond is either polar covalent or nonpolar covalent, we need to use the electronegativity chart on the back of page 8 of your reference guide. So it looks like the periodic table. Some of you tried to use it like the periodic table, but instead of atomic masses in it, it has electronegativities. In fact, F will have a 4.0, and then there are other numbers in there, in the other boxes, okay? So try to find that one right now. Okay, we are going to do I'm going to draw a little differences in electronegativity chart. Okay, so you're going to need this information to calculate whether a bond is polar or nonpolar. So we're going to draw a little line here. Kind of like a number line from math, only not quite, but almost. And put the cutoffs here. Now, I'm going to do it like you would in math. Obviously, if it's a closed circle, it includes those numbers. Okay, and we're going to color into here, more or less. Okay. Now, this area is nonpolar, this area is polar, and this area is ionic. Now, differences means you subtract the two numbers. So, you need to subtract the two electronegativities. And then if your number is less than 0.4, but not including, okay, then your bond is nonpolar. Okay, if when you subtract the two, you get either somewhere between 1.4 or 0.4, sorry, and 1.7, your bond is polar. Okay, I'm gonna move this up. Now, if your bond is greater, or if the difference is greater than 1.7, your bond is ionic. Huh? What are we talking about? I'll show you in a few minutes. But we will refer back to this chart, so please don't lose it. Okay, now polar covalent bonds. Let's talk about them first. One atom hogs the shared electrons more than the other electron, or more than the other atom. Now remember, these guys are sharing electrons. They're not taking electrons. That would be ionic. So they're just sharing them. So if one atom hogs it more than the other one, then it's probably a polar bond. One atom is more electronegative than the other one. Now, when we have this type of situation, we label each atom as either slightly negative or slightly positive. Yes, that's a really funny looking, it's a Greek letter. I don't remember the name of it, but yeah, that's how we do it. We use that funny little symbol. In fact, let's look at OH. Okay, so we have O and H. Now, when we look up on the table of electronegativities, we find that O has an electronegative value of 3.5. Hydrogen is 2.1. Now we're going to subtract those two numbers, and we get 1.4. Okay, so that tells us that it's in the range of polar. So this is a polar covalent bond. Now, since it's a polar covalent bond, we have to put that funny looking positive and that funny looking negative on top of each one. So this one is slightly negative and this one is slightly positive. And that's because the slightly negative one is the atom that's more electronegative, which means it's going to have more of that electron cloud. So it's more electronegative than the other one. Okay, so Obviously, the slightly positive one goes on the one that's less electronegative. Okay, let's look at nonpolar covalent bonds. They are the equal sharing of electrons. Both atoms have the same electronegativity values or extremely close. Usually, this means they're the same one, but not always. So, okay, let's look at F2. Obviously, it's the same atom. So they are going to share the electrons equally. And if you subtract the two numbers, guess what? You get 0. Yay! So anytime you have two of the same atoms, it is always, and I mean always going to be nonpolar. Okay, now let's look at pH. Phosphorus and hydrogen. Now when we look up on the table of electronegativities, phosphorus is 2.1, and guess what? So is hydrogen. When you subtract that, you get 0, so it's nonpolar. Okay, since there are two types of covalent bonds, that only makes sense that there are also two types of covalent molecules. So not only do we have polar and nonpolar covalent bonds, but we have polar molecules and nonpolar molecules. Now, whether a molecule is either polar or nonpolar depends on their shape and the kinds of atoms around the central atom. It doesn't have anything to do with the electronegativities. That just tells you whether a bond is polar. Now, you could have two polar bonds, each on one side of the central atom. So, but then they equal each other out. That makes it, that atom is probably going to be nonpolar at that point in time. Okay, so nonpolar molecules. There's the same kind of atom around the central atom. And I can't stress that and enough, the shape has no unshared pairs, or the dots, of electrons on the central atom. In fact, it has one of these three shapes. It's either linear, trigonal-planar, or tetrahedral. Those are the three shapes that are nonpolar shapes, okay? So if it's one of those three shapes and all the atoms around are the exact same kind of atom, then you have a nonpolar molecule. Polar molecules, on the other hand, are a little different. There's different kinds of atoms around the central atom, or the shape contains unshared pairs, in other words, there's dots on it, of electrons on the central atom. And these are the two polar shapes, bent or trigonal pyramidal. Okay, CO2, we need to draw it first. When we draw it, we should get something that looks like this. Now this shape is linear, so this is a nonpolar shape. So what we have to do is look at the central atom and find out what types of atoms are around the central atom. In this case, we have oxygen. So they're both the same. So because both are the same, this is a non-polar molecule. Okay, pretty easy, right? So we have both the same kind of atom around. I'm going to put it around center. And it's a non-polar shape. Okay, so that makes it nonpolar. Okay, now let's look that. Now let's look at NH3. Can't talk tonight, guys. So we're going to put our N here, our H's and H here, and we have two dots. Now this is a nonpolar shape. It's trigonal pyramidal. Because it's trigonal pyramidal, guess what? That makes this, makes this a polar molecule. So we don't even have to look. It doesn't matter that there's all the same kind of atom around it. The fact is, it's trigonal pyramidal. That automatically puts it at polar. Okay, so let's look at CH2O. When we draw it, we get something that looks like this. Now, if you look at the shapes, this is trigonal planar. Now, trigonal planar, oops, let's see, you know what? think I'm going to write that a little bit better. There. Trigonal planar. Trigonal planar is a nonpolar shape. So I'm going to put nonpolar shape. But if you look, guess what? Those are not the same. So they're not the same kind of atoms. Because of this, this is a polar molecule. Well, what's happening is that oxygen is definitely going to pull more on that electron cloud around the carbons than those hydrogens will. So it's definitely a polar molecule. Okay, that's it for tonight's notes. All I can say is hopefully you understand this. If not, we will be doing a warm-up tomorrow after the quiz. Yes, you're going to be taking a quiz on the molecular geometry, so hopefully you completed the activity, you did your homework, and you understand it. So I guess I will see you tomorrow.